generous introduction. I'm going to get my screen up, and please let me know if you can't see it. It appears I do not have the ability to share my screen. Michelle, could you hand it over, please? Okay, great. So please let me know how this is. So today, as Joanne mentioned, we're going to talk through a few different things. Namely, we're going to take a tour through modern data as an introduction to modern data. We're going to talk about a few case studies and then give a few recommendations for how to navigate economic uncertainty given the backdrop of all the information from the first few sections. And to start, what is going on with modern data and modern data science? We'll go through some terminology to make sure everybody is on the same page, and then we'll go into examples. So data science is new only in that it combines old fields in a new way. Data science was a term that existed 10 years ago, but all the principles that apply to it have for a very, very long time. We know exactly what that means, starting with the technology. So in order to do anything with data, you need data. And this comes from what we call data sources. Examples at your companies probably include a CRM, customer relationship management tool, point of sale POS, a website or an application if you have that, or if you're in healthcare, an electronic health record system. Then in order to get that data from those sources, the CRM and the point of sale, to a place that you can actually use it, you build data pipelines into something that's called a data warehouse, or more generally, a database. Then one of the outputs of this data source is what we call human analysis. And this takes the form of email reports, dashboards, and analyses. So, think an Excel analysis or Tableau analysis. And then another, and maybe what's getting the most attention these days, is what I'm generally calling machine analysis. And we'll dig into exactly what that means. Quick parenthetical, you don't just need a data warehouse or database in order to do machine analysis type things. This can be done directly in websites and applications. You're familiar with this through Netflix and Amazon and other sites. And also hardware devices. We're seeing this increasingly in industrial supply chain, in medicine, where devices are being given machine learning capabilities so they can predict things like when a patient is going to become sick, or when a hardware component in a factory piece of equipment is going to fail. All right, so that's the technology part of it. Then what about the people? Who are the people who are actually doing this stuff? So there's a thing called the data engineer, and they're responsible for the data pipelines, moving data and cleaning data so that it can be used later. Then there's a person called an architect, and you can think of the relationship between architect and engineer the same way you would on a building site. Somebody designs the entire building, and then somebody does the implementation execution. Then after the building is built, there's somebody who actually does the analysis. They're called the data analyst, and that's usually manual. But you can also give the data to a machine. And there's somebody called the machine learning engineer who writes the code that teaches a machine how to semi-autonomously use the data. And then there's the term data scientist. So what does that mean? And sometimes people use it to mean data analyst. Sometimes they use it to mean machine learning engineer, and sometimes they use it to mean data engineer. And really what that says is it's a catch-all for a lot of different things. And then finally, I said that we would focus on the machine learning part of this slide. It's because there are a lot of big words that surround it, and some of them mean different things, some of them mean the same thing, but we'd like to spend some time demystifying that. So artificial intelligence, what is that? Machine learning, is that different or the same from artificial intelligence? What is deep learning? So really quickly, throughout the presentation, since we're going through a lot of technical content, I wanted to make sure that that attendees had the opportunity to ask questions. So if you have questions, please write them into the chat box. Michelle will triage them. And if some of them are blockers to understanding the content of the presentation, we can pause and talk about them. So Nichelle, I'll trust you to jump in and let us know if there are any questions that seem really important to understanding the content of the presentation.
Will do, Charles.
Thank you. So we're going to jump into big words. The AI, the data science and machine learning, the big data, what does it all mean? And we'll take it apart piece by piece. So at the very core of data work or data science and all this stuff is a mathematical model that represents the world. You're familiar with this. We all took our Wharton Stat 101 class. This is a linear regression. It's a model that says X and Y are related by a straight line. You fit a line through the data points and you can predict Y. Here's another model that we were taught. This is a clustering algorithm. It finds groups of data points in a space and it identifies them. So this is like customer segmentation. So you put the mathematical model into a computer and you give it a data feed. And then it starts self-updating. So as the model gets more data, it learns new things about the world. It learns about new customers, it learns about new sales, it learns about new conditions. And that generally is the process of machine learning. Some examples of this include movie recommendations, component failure in hardware, customer churn, which customers are going to leave you, propensity to buy, which leads are most likely to buy, stock prices, flight prices, which team is going to win sports, many more. Okay, so we just talked about machine learning. What is AI? This is loaded. So within machine learning, there are a lot of different types of machine learning mathematical models that you can use. We talked about linear regression just now, and there's something else called a tree-based model, which uses a different architecture. And finally, there's something called a neural network. So the pros of neural networks are that they're extremely flexible and they capture complexity and nuance in a way that other models can't quite as well. However, they're very expensive computationally with large amounts of data, which is where they really excel. But over the last decade, something changed. Neural networks have been around since the 1960s, but we finally got enough data, and there are improvements in computational hardware that enabled this specific type of model to work. And so whereas before a neural network could do something like classify handwriting on mail. So this is actual examples of handwriting that were transcribed for a computer, and then the computer would identify each number, 0, 5, 0, 8. But because of these improvements in computation, you can now do things like process the image of a cat or identify a cat or a flower. And the improvement on the neural network technology is called a deep neural network, which is deep learning. So deep learning is really the most recent implementation of this very advanced algorithm that was only enabled because of all this stuff. So the question is, why does that matter? So one side note is that when people are talking about deep neural networks and deep learning and they're also talking about artificial intelligence technically, is what people mean. We'll go into what else artificial intelligence means in a moment. Some examples include image classification. You'll notice that in Google, there are tags that are assigned to words, and behind each of the pictures, Google's image classification engine is looking at every image and saying, okay, what is the likelihood that there is a bus in this picture? There's a yellow object. Is it bus shaped? What about trees? What about bushes? What about a dog? And so this application has gotten really big because, again, the algorithm is available, data is cheaper. Language translation is a good one. There's a great article written about how deep learning enabled Google to dramatically improve the quality of its translations about 3 years ago. And then finally, voice recognition, apps like Siri and Alexa, also using deep learning. And why deep learning? It's because with enough data, these models improve really well. And then last point, these days, because machine learning and artificial intelligence and all of that have gotten so big, and artificial intelligence is a fancier, more accessible word than machine learning, what's happened is people use artificial intelligence and machine learning interchangeably in a business context. that was a lot of stuff. Quick recap. Machine learning is the blanket category of machine intelligence models. Within that, there's a type of model called artificial intelligence models or deep learning. But colloquially, it can be used to mean machine learning or deep learning. And then finally, data science, just modern data techniques. It's the broadest category of all of them. Great. I'm going to pause for a moment. I know that was a lot of content. If you have any questions, please drop them into the chat box. Great. I'm going to assume nothing for now. Please let me know if I missed anything. So a few case studies to put examples to all this stuff that we're talking about. The first case study is fighting churn with machine learning. So one of the companies that we worked with has about 100 employees, 17 million in funding post Series A, and they're a marketing and fraud technology company. Specifically, they take data from the internet and they enrich it with a bunch of attributes about that site visitor. Figures out what company they belong to, gives you metadata about the company, metadata about the individual. And the problem they came with was that they were growing really quickly. They'd raised a Series A and they were doing well. And as part of that, they needed to manage their churn because improving retention, it's one of their stats, improving retention by 5% can boost profit by up to 95%. It's from Bain, we didn't say it. And the process that they wanted to use was this. So in the white box is all the data that they have. There are attributes about their customers who paid for their product, data about the communication with the customer management data, and then finally, the way the customers used their product. And then using all of that data, about 400 variables in all, we were able to develop a predictive model that sorts customers into either happy or at risk of churn. And if they're at risk of churn, then you can flag them for the customer support team. And they'll know that the model thinks that this is a very high-risk customer. So altogether, it used 400 variables. And the outcomes were really interesting. They had a really large customer list. And of all of the customers that would leave in the future, 75% were correctly identified by the model. What's really interesting about this is the model ended up focusing on the long tail of revenue. So there's some customers that are really obvious are going to leave you. They're really big, they make a lot of noise, they're important clients. But it actually turned out that in the human process of identifying companies that were going to leave, that the success managers were often ignoring the much smaller customers, and many of those were also subject to leave as well. So there's an additional 40% of long tail revenue recoverable through this model. And then finally, the company doesn't release revenue numbers, but a quote from the stakeholder there was hundreds of thousands of revenue saved. Another example using machine learning is machine learning-based product pricing. So the company was about 250 to 500 employees with $250 million in funding, and they're an enterprise software company. And they came with this problem that they want to come up with a new enterprise pricing plan to remain competitive and because they're releasing new products. They had 5 years of data and hundreds of contracts of data. And the problem here is in analyzing all of that data, the enterprise sales process is highly variable because it's people negotiating against other people on these really big, often multi-year contracts. So the question is, how do you put some numbers to it? Can you do it with pivot tables? Can you do it with a Tableau dashboard? This is a really good candidate for machine learning because it can find the hidden patterns that are buried in data and help you control some of the variability. And so the question here is, what is the implied value of different product features so that in the future pricing plans, that you at least have some sense of what people are willing to pay for the product? And so one of the first problems that we had to solve in this was figuring out what is every individual's price sensitivity to the product. And to do this, it took 1,000 samples of the data set and made 1,000 predictions to come up with a whole range of what we think the customer could have paid, given what we knew about every other customer. So essentially like a fair value for what they would have paid. And then they went through a bunch of different configurations, 100,000 different combinations of pricing package configurations to back test on their existing customer list. So what you see over here are the different scenario names. These are things like customer lifetime value across the entire customer set, the predicted revenue if the customers were to go back in time and buy their contract for the first time again, et cetera. And the net result of this was going to be launching this quarter. We're really excited about it. But what the model tells us is that we're aiming for a 13% increase in LTV across for customers who experienced the new pricing plan versus those who didn't, while also being aware that you're making a sacrifice in pricing sensitivity, essentially that you're going to push the boundary by about 13%, but you know that you're pushing that boundary, and that's the important thing, mitigating the uncertainty. And then finally, a simpler non-machine learning based example is developing a 360-degree view of your customers. So the company for this was about 50 to 100 employees. It's a marketplace with about 400,000 buyers and 2,000 sellers. And the problem is that they had data all over the place and it wasn't verified. So when people were looking at it, they weren't sure whether or not to trust it. And also, this is really important for the marketing team, attributing marketing spend to actual sales dollars was a really manual, weeks-long exercise for analysts. And so the solution for this is take into account all the data sources that relate to viewing your customer. So this includes paid advertising, email marketing, website usage, and other things. And centralize it in a database. So you put all of that in a single place, put in some checks, and do some data processing to make sure that the data is clean and trustworthy and that when people are looking at it, they know they can trust what they're looking at. And then put on an analysis layer on top of it. So you get your charts and graphs and you can see it quickly. What's the net outcome of something like this? Every analyst has started saving 5 analyst days per month. Of course, this is at the cost of engineering days because you do engineering work to make up for you do upfront work to make up for all this back-end work. And everybody who is looking for data was able to find it without having to ask themselves whether or not they trust it. Comprehensive views of their customers. And then finally, this is really nice verbatim. I can trust my numbers. That just feels nice. Okay, great. I'm going to pause one more time. A lot of different things there. Okay. And then finally, what is some recommendations? So you got a really nice survey of the data landscape, the different components of it, the people who work in it, names of different methods, and some examples. So what do we actually recommend to people these days? So I'm going to start by sharing a couple of Pareto principles or 80-20 rules that we use in data science. So one, a lot of these projects are a lot of data cleaning. It's really dirty and very little analysis. So if you end up embarking on these things, don't be surprised if you end up waiting 3 weeks, a couple of months for something to happen. And then all of a sudden, all this analysis happens and you have a machine learning model. The other thing is that, getting a model, a machine learning model or an AI model to work, getting it to work initially takes some effort. You'll get about 80% of the way there, but for a lot of applications, that's not good enough. So for example, when Netflix is making recommendations, well, maybe it can be kind of okay. But when you're in a hospital setting and you're trying to predict whether or not somebody is sick, whether or not somebody is okay, you need to make sure that model is really good. And so usually the rest of the performance for high stakes models, usually dealing with either dollars or health, come towards the tail end of the project. And here's a really dirty secret. You don't need super advanced models to solve the majority of problems. Actually, I'd say the simplest models solve the majority of the machine intelligence problems out there. And then Finally, and this, it probably isn't something we should say, but 80% of problems can be solved fine without data. Some people get excited about it and they reach for data as a tool, but we, in a lot of cases, don't recommend data as the solution to a problem. So those are some general rules. And then finally, the question is, what given all of that, have we been recommending these days when it comes to thinking about data projects, especially when there's an uncertain economic outlook, especially when people are trying to be more efficient? Um, Here's a great place to go: the machine analysis stuff. The reason is that it's low effort, it's very measurable value, and the payback period is relatively shorter because you can see immediate improvement in decision making if it's a BI application, and maybe a little bit later getting into process automation. But in general, they're really good low hanging fruit for environments where there's belt tightening, there's a lot of uncertainty, and people are looking to be more efficient. Then the other, but slightly longer term type of project that usually works really well is um, creating the data infrastructure piece. So it's medium high effort, it provides predictable value, but it has a much longer payback period in terms of process automation. So again, we usually recommend going to the first one. And for now, we wanted to first say thanks to the entire team for having us here, and also go into the next segment of tonight's discussion.